So let's look at an example. The center and radius. Find the center and radius of the circle. X squared plus y squared minus 2x minus 6y plus 1 is equal to 0. So the radius squared is 1/4 of the square of the f term, which is -2. So we have 1/4 -2 squared, plus 1/4 of the g term squared, which is -6 squared, minus h. And so this is 1/4 of 4 plus 1/4 of 36 minus 1. 1/4 of 4 is 1, so 1 minus 1 is 0, and so we're left with 1/4 of 36, which is 9. And so the radius is the square root of 9, which is 3. And the center of the circle is given as the point -1/2 of the f term and -1/2 of the g term. So this is -1/2 of -2 and -1/2 of -6. And so this is the point 1, 3. So the previous theorem gave us a simple way to determine the center and radius of a circle when the circle is given in its general form. So as an exercise, determine the center and radius of the circle 3x squared plus 3y squared minus 12x minus 48y is equal to 0. All right, so next we'll prove a lemma. The shortest line segment from a point to a line is the perpendicular. So proof. So we have a point P and a line L. I want to show that the shortest line segment is the perpendicular from the point P to the line M. And we'll call that point of intersection to the line L. We'll call that point of intersection M. So consider any other point Q on the line. Then, by the Pythagorean theorem, we have that PQ squared is equal to PM squared plus MQ squared. And so PQ is the square root of PM squared plus MQ squared. And this is strictly greater than the square root of PM squared. And the square root of PM squared is PM. That is, the line segment PQ is greater in length than the line segment PM. And therefore, the shortest line segment from a point to a line is the perpendicular. And because of this fact, we define the distance from a point to a line to be the perpendicular connecting the point, the perpendicular line segment connecting the point to the line. Distance from a point to a line. Okay, so now we'll use the lemma we just proved to prove a theorem. A tangent to a circle is perpendicular to the radius which is drawn to the point of intersection. So proof. So given a circle, we'll draw the radius to the point of intersection. And so the tangent line at the point of intersection we want to prove that this is perpendicular. So since, and we'll call the point of intersection with the line L, M, since OM is a radius of the circle, it is the distance from the point O to the line L, and hence that line segment OM is perpendicular to the line L. So now we'll prove a related theorem. A line that is perpendicular to the radius of a circle at the point of intersection is a tangent. So proof. So this time we start with the assumption that we have a circle and we have a line that is perpendicular to the radius of the circle at the point of intersection. And we'll call that point of intersection M. So let Q be any other point on the line L. Then by the previous lemma, the line segment PQ is greater than the line segment OM, which is the radius of the circle. And so the point Q is not on the circle, and hence the line L intersects the circle at exactly one point. And therefore, the line L is tangent to the circle. Okay, so new definition. Two circles are orthogonal if their corresponding tangent lines at the points of intersection form right angles. So next we'll prove another theorem. This is known as the test of orthogonality. Okay. So two circles, which we'll call C1, which is a set of all points x, y, where x squared plus y squared plus f1 of x, not of x, f1 times x, plus g1 times y minus h1, plus h1 equals 0. And the circle C2, which is all points x, y, such that x squared plus y squared plus f2 times x plus g2 times y plus h2 is equal to 0. These two circles are orthogonal if and only if the sum of products f1 times f2 plus g1 times g2 is twice the sum of h1 plus h2. So proof. First, let's construct two intersecting circles. And we'll give one of the points of intersection let's call that circle 1. And we want a second circle. And we want to look at their intersecting tangent lines at the point of intersection. And we'll call this circle 2. So when we have two circles that intersect at a point, their corresponding tangent lines will intersect, and we'll call the center of circle 1A and the center of circle 2B, and the point of intersection we'll call P. And so we now have a triangle APB. Now the center and radius of the circle C1 is -1/2 F1, -1/2 G1, and the square root of 1/4 F1 squared plus 1/4 G1 squared minus H1, and the center and radius of the circle C2 are -1/2 F2, -1/2 G2, and the radius is the square root of 1/4 F2 squared plus 1/4 G2 squared minus H2. So suppose that C1 and C2 are orthogonal. Then the angle APB is a right angle. And so triangle APB is a right triangle. So we have that AB squared is equal to AP squared plus BP squared. Now, AP is the radius of circle 1, and so AP squared is 1/4 F1 squared plus 1/4 G1 squared minus H1. And BP is the radius of the second circle, and so BP squared is 1/4 F2 squared plus 1/4 G2 squared minus H2. And also we have the distance between A and B. We know the center of circle 1 and circle 2, which are the points A and B respectively. And so the square of AB is the difference in the first coordinates, which is -1/2 F1 minus a -1/2 F2, so that's plus 1/2 F2 quantity squared plus -1/2 G1 minus -1/2 G2, so that's plus 1/2 G2 quantity squared. So if we expand this, we get 1/4 F1 squared minus 1/2 F1 times F2 plus 1/4 F2 squared. If we expand this second term, we have 1/2, correction, 1/4 G1 squared minus 1/2 G1 times G2 plus 1/4 of G2 squared. So again, looking at this equation, AB squared is equal to the sum of squares of AP squared and BP squared. And so if we eliminate like terms, we have that negative 1/2 of F1 times F2 minus 1/2 of G1 times G2 is equal to negative H1 minus H2. And so eliminating the negative signs, we have 1/2 of F1 times F2 plus 1/2 of G1 times G2 is equal to H1 minus H2. And so if we now multiply both sides by 2, we have that F1 times F2 plus G1 times G2 is 2 times the quantity H1 plus H2. So conversely, suppose that this equation holds that F1 times F2 plus G1 times G2 is twice the sum H1 plus H2. Then we have the triangle APQ, APB is a right triangle. And so the measure of angle APB is pi by 2, and hence circle 1 and circle 2 are orthogonal. And therefore, circles C1 and C2 are orthogonal if and only if the sum of products F1 times F2 plus G1 times G2 is twice the sum of H1 plus H2.